So in this video, I will explain the principle of least action, which is a physical law that governs the movements of mass objects in our universe. It will be a transcendental explanation in terms of requiring you to think out of the ordinary empirical experience. It will help you to build an intuition on the principle rather than dumping the mathematical formulas about this principle. If you open any other video on principle of least action, most of them will explain the principle in this routine. First, they will describe a simple problem about the movement of mass object through the space. They will have a start point and end point, and they will draw the real trajectory. They will define a function s, which takes any trajectory that is passing through the start point and end point in the space as an argument, and it returns a number, which will be the action. And since the real trajectory follows the list of the action, if you perturb the real trajectory by a little bit by a random function eta, also defined as every time point t, which using this eta function perturb the real trajectory a little bit, the perturbation should be equal to 0, because since the real trajectory is at the minimum, its first derivative is 0 at every point. So this delta s, which is the real trajectory perturbed by some random small function eta t minus the real trajectory, will be 0. Then they will teach you this mathematical trick, which is called integration by part, which can be used to solve this delta s equals to 0 problem. And after you solve it, it will yield the Euler-Lagrangian equation. If you substitute the Lagrangian with the kinetic energy and the potential energy terms of the problem, we will get the classical mechanics. But we will not do this in this video. So I think to understand the principle of least action, you should think out of the ordinary empirical experience and picture yourself as a designer of a universe. You can design the physical laws in this universe. An action, as a quantity in physics, is actually a tool to describe different worlds. So there is nothing special about our world. In another world, the movement of the mass object does not necessarily follow the list of action. It could follow any other action. So action can be used to describe different worlds. It actually reminds me the lesson of Copernicus. At his era, no one believes that solar is actually the center while the Earth is rotating around the sun. Everyone thinks the Earth is special, which is similar in our modern era. If I tell you that there is a world where the movement of its object does not follow the principle of least action, you'll probably think it's impossible. Third, to under this principle, I think you also should forget about the law of energy conservation. Because the law of energy conservation, as we shall see, is just an accident of the fact that our world follows the principle of least action. If the movement of the objects in our world follows any other action rather than the least of the action, the energy will not be conserved. So to start to explain this principle, I will turn to I think the most simple problem about the movement of bodies through space and solve the action concretely for several different trajectories, and then hopefully could give you some intuition about this principle. So what is the problem? The problem is actually the movement of ball that is falling to a planet. It's very simple to the common experiment where you drop a ball and the ball falls to the ground. More formally, the problem is a ball with mass m is dropped near a planet at t equals to 0, x, which is the position, equals to 0. And after TO, it is found at x equals to XO. And there's the relationship between XO and TO, which is that XO equals to 1/2 the GTO squared, where G is arbitrary positive constant. Please design a trajectory. So in this problem, you only see the starter point, t equals to O, x equals to O, and the end point, t equals to TO, and x equals to XO. And you need to design a trajectory that passing through the starter point and end point, and also write out the physics about the trajectory. Because there is a infinite possibility of trajectories passing through 2 points, we need to have some constraints on this problem. This is a prerequisite of what is known about the world where we are trying to design a trajectory for a starter point and end point. So in this world, it has space x, it has time t, and it has matter, and matter has mass, which is designed as m. Velocity is solely defined relative to space and time, which is the derivative of position with respect to t. The kinetic energy is defined as 1/2 m velocity squared. And near the planet, an object has the potential energy defined as minus mgx. So this is all we know about the physics in this world we are trying to design a trajectory for. Please forget any other physics you know, especially the law of energy conservation. So given what is known about the world, we are still left an infinite number of possibilities of trajectories between the start point and end point. So to make the problem simpler, we only consider 3 trajectories, and we will choose one of the 3 trajectories as real trajectory in this world. So let's see what are the 3 trajectories. The first trajectory, the blue line, in this position time graph, the PD graph, the x-axis is time, the y-axis is the position. So the first trajectory, the blue line, is the constant motion from the start point to end point. So it has the velocity xo divided by to. Since xo is 1/2 GTO squared, it has the velocity 1/2 GTO. And the position as a function of time is the velocity times t, which is 1/2 GTO-t. For the second trajectory, which is a green curve, its velocity increases with time with a factor of g. So at any time point, its velocity will be gt. And the position function will be an integration of velocity over t, which will be the 1/2 gt squared. For the third trajectory, before half to, its velocity is 0, and after half to, its velocity will be a constant number, which will be the xo divided by half to, which is gto. Given what its velocity is for the third trajectory, we can calculate its position function. So before half to, its position is 0, and after to, its position is gtot. So this is the physical formulas for the 3 trajectories. Both the velocity function and the position function are given. So let's look at what the 3 trajectories look like in an animation. So the first trajectory, after the ball is released, it follows a constant motion to the end point. For the second trajectory, after the release of the second ball, it starts with 0 velocity, but gradually accelerates until to the end point. The acceleration is by a factor of g. For the third trajectory, after the releasing of the third ball, it stays still for half to, and after half to, it follows a constant motion to the end point. So what I want to emphasize here is, given what is known, all the physics we know about this world, all the 3 trajectories are possible. There's no reason to favor one trajectory over the other. And obviously, the first and the third trajectories do not follow the law of energy conservation. Because if we look at this PD graph, the first trajectory in the PD graph, we can see throughout the trajectory, its kinetic energy is constant while its potential energy changes. So the energy in the first trajectory is not conserved. But it's valid given what we know about the world so far. So how do we choose among the three trajectories? Well, as a designer of the universe, you can basically just choose whichever you like. But here, I just list one way to choose among the three trajectories. So you first you define an arbitrary quantity, a rather arbitrary quantity, which is kinetic energy minus the potential energy, and you call it Lagrangian. It's just an arbitrary quantity. And then you decided for the three trajectories, you will choose the one with the smallest integration of Lagrangian over time. And you call this integration the action. I want to underscore here that you should think this as a rather arbitrary decision to choose this form of Lagrangian and choose this form of integration as an action. So this is the decision we will follow to decide which trajectory to use as the real trajectory in the world we are currently designing. So given the formula in the previous slide, we can calculate the action for trajectory 1. So it's an integration of the kinetic energy and minus the potential energy. Substitute the velocity and the position function in this integration. You got this term, and you do the integration, and you calculate the action for the trajectory 1 is 3/8 mg squared TO cubed. Similarly, you can calculate the action for trajectory 2. You substitute the velocity and the position, and you do the integration, and you calculate the action of the trajectory 2 is 1/3 mg squared TO cubed. The action of the trajectory 3 is calculated similarly, but here, as defined in the previous slide, the trajectory 3 is a piecewise function, and its non-zero part is defined between half TO to TO. But it is mathematically equivalent to this integration from 0 time point to half TO. It's just simpler to calculate the integration this way rather than to integrate from half TO to TO. So it's mathematically equivalent. So if you do this integration, you calculate the action of the trajectory 3 is the same as the action of trajectory 1, which is 3/8 mg squared TO cubed. So this is a summary of the actions of the three trajectories. The first column is the integration of the kinetic energy over time. The second column is the integration of the negative potential energy over time. The third column is the sum of the first column and the second column, which will be the integration of Lagrangian over time, which is the action. From this table, we can see that the first trajectory has the smallest kinetic term of the action, while have the largest potential energy term of the action. The third trajectory, in contrast, has the smallest potential energy term of the action, while has the largest kinetic energy term of its action. For the second trajectory, both its kinetic and potential energy terms are in between the first and third trajectory, but overall, the sum of its kinetic terms and potential energy terms is the smallest among the three trajectories. So based on the decision we made in this slide, we will choose trajectory 2 as the real trajectory in the world we design. So this is actually how to choose a trajectory that is following the list of the action. You basically calculate this integration and pick up the list of the action. So let's think about the calculation of the action more intuitively. In fact, the calculation of the integration of the negative energy over time can be expressed in such forms for all the three trajectories. So in all these three forms, we can say the integration part is actually the area under curve of the three trajectories. So in general, it can be expressed as a constant mg times the area under curve of the trajectory in the PT graph. So the area under curve of different trajectories are proportional to the negative potential energy term of their actions. So by solely comparing the area under curve, we can easily tell that the third trajectory has the smallest negative potential energy term of its action, while the first trajectory will have the largest negative potential energy term of the action, while the second trajectory has a negative energy term in between the first and the second trajectory. So when we learn physics, we know that an integration of velocity over time is actually position. When I first learned physics, I often think, what is the integration of position over time? So at least in this problem, we can say that the integration of position over time is somehow related to A. Specifically, it is proportional to the negative energy contribution to the action. So that is one way to think action. It's proportional to the integration of position over time. Similarly, we can do the same thing for the kinetic energy term of the action. The kinetic energy integration of the trajectory can be expressed in a similar form as 1/2 mg squared, which is a constant, multiplies the area under curve of this function. This function is actually v squared divided by g squared, and while v is a function of time t. So if we plot this function with respect to t, we can got these v squared curves for all the three trajectories. And from this graph, we can easily tell from the area under curve that the first trajectory has the smallest kinetic energy term of its action, and while the third trajectory has the largest kinetic energy term of the action, while the second trajectory has a kinetic energy term in between the first and the third. So this is some intuition about the kinetic energy term of the action. It's also simply an area under curve. Taking both graphs together, we can think action rather visually. So first, for any trajectory, not limited to these three trajectories used in our examples, we can plot it in the PT graph. And after we plot it in the PT graph, we can calculate its first derivative at every point. And that will be the velocity at every point. With the velocity calculated, we can plot this v squared t graph of the same trajectory. Then the action of that trajectory will simply be some constant multiplied by the area under curve of its curve in this v squared t graph, plus some constant multiplied by the area under curve of its curve in the PT graph, and the sum will be the action of its trajectory. We can intuitively think it as a compromise between the area under curve in the PT graph and the area under curve in the v squared t graph. If you want a small area under curve in the PT graph, the slope of the trajectory will be high, and the area under curve in this v squared t graph will be large. If you have a large area under curve in the PT graph, the slope of the trajectory will be small, and the velocity will be small, and the area under curve in the v squared t graph will be small. So it's really a compromise between the two choices, and the green curve is actually the best compromise and will be the least of the action. Next, I want to talk something about the constant motion, as we have calculated in the previous slide that the first curve has the smallest integration of kinetic energy over time. So if our problem does not have a potential energy term, if it's far away from any planet, the Lagrangian will only have the kinetic energy term, and the first trajectory will have the least action. So this is actually what exactly happens in our world when there is no other forces applied to a mass object. It will follow the constant motion, which will be the blue curve. Next, let's think about more interesting trajectory, which is a teleport. So in this trajectory, the ball stays still until half TO, and after TO, it teleports to the end point, and then stays still until TO. So before the definition of action in this slide, given what is all we know about the physics in the world we design, teleport is allowed. It's as valid as all these three other trajectories we have discussed. And it looks like if we move the teleport point to the end TO, it will have zero kinetic term and also zero negative potential energy term. Its action looks like to be 0, which will be smaller than trajectory 2. So is it really the case? So before we dive into the detail of the teleport, let us think about another trajectory, trajectory 5. It's very similar to trajectory 3. The only difference is that the point where the ball starts to move is 1/nth TO away from TO. So these are the formulas that give out the velocity and the position function with respect to time. And we can calculate the action very similarly for the trajectory 5. And we can see when the n approaches infinite, the action of trajectory 5 approaches infinite. Specifically, it is the kinetic component of the action that approaches infinite. The negative potential energy term of the action actually approaches 0. And if you look at this trajectory, when n approaches to infinite, TO times 1 minus 1 over n approaches to TO, which will be the situation of teleporting at TO. Which this calculation means the teleport will have the infinite action. For trajectory 4, it should also have the infinite action. So it actually makes sense because when the ball is teleporting at half TO, it moves a certain distance using 0 time. So the velocity will be infinite. The kinetic energy, which is proportion to the squared velocity, will be even more infinite. So it makes sense its action to be infinite. That's why teleport is not allowed in our world. Finally, I think many people would like to think the principle of this action as something of the principle of list conversion, because Lagrangian, which is kinetic energy minus potential energy, seems to indicate it's a conversion between the two forms of energies throughout the trajectory. So to follow the list of the action is follow the list of conversion. But I think the concept is basically wrong, because when you say the real trajectory is following the list of the conversion, you mean that for other trajectories that do not follow the list action, they also have conversion, but only that their conversion between the two forms of energies are not the least. But if you look at the trajectory 1, during its trajectory, its kinetic energy is constant, and while its potential energy changes, you cannot say there's a conversion between kinetic energy and potential energy, because their sum is not conserved. Only at the condition that the energy is conserved, you can say two forms of energy are converted from one to the other. But the very fact that the law of energy conservation is the outcome of principle of list action, which does not apply to other trajectories. So, in conclusion, an understanding of principle of list action as principle of list conversion implies law of energy conversion in all possible trajectories, which is actually not true. So to me, I think it's better to think the kinetic energy and potential energy components of the action as rather separate beings. So during the real trajectory, the integration of the kinetic energy is minimized while the integration of potential energy is maximized. That's how we should think about the action. So why principle of list action? So in the previous slide, we have described the decision to use the principle of list action to decide among trajectory as an arbitrary decision. So why it has to be the principle of list action? First, I want to say that this question is out of physics. It's more like philosophical, because physics only teaches us of how the universe works, but it does not answer why the universe works in this way. So that's another reason why this video is somehow a transcendental explanation of the principle of list action. I think the problem can be broken down into three questions. The first is why it has to be the least of all possible actions. And the second question is why the action has to be an integration of Lagrangian over time. The second question can be further divided into two questions. First, why action has to be an integration of something over time. And the second question is why the something has to be the Lagrangian defined as kinetic energy minus the potential energy. I think all we have said in this video lies a very good foundation to explain the first question as why the movement of the mass object has to follow the least of the action. Let's think about the alternatives. It can't be the maximum of the action because it does not exist. The maximum of the action could be infinite, as we saw in trajectory 4. And if we choose any other numbers higher than the least of the action, for example, in the example we used to explain the principle, if we choose the action of the trajectory 1 of the trajectory, which is 3h mg squared TO cubed, for this very number of action, there are two trajectories. So when you choose a trajectory based on its number of action, you want the trajectory to be unique. You want only one trajectory that has this number of action. So it looks like only when you choose the least of action, the trajectory is unique. So if you plot all the possible trajectories in the x-axis and the action as a y-axis, you'll probably get a curve like this. It has a single minimum, but at any other level of action, there will be more than one trajectory. So to be unique, a trajectory's action has to be the least. Next, why the action has to be an integration over time? I think this is a very simple question because trajectory is a continuum of positions defined over time. As something defined over time, if you take that as an argument, the action also has to be some integration over time. I think the last question is the most fundamental, why Lagrangian has to be kinetic energy minus potential energy. Actually, I don't think I have a satisfying answer to this question. Probably no one does. But I have some ideas why it couldn't be something else. But it's not so relevant to the material presented in this video. So I'll probably make another video to illustrate what I'm thinking about this question. If you have some insights, please post in the comments. Next is an exercise. Actually, this is I think the classical problem when people are explaining the principle of least action. So it will be a good exercise to do some calculation on the action and sort out what is the least of the action. So the exercise is in the same world as the problem we have presented in this video, near the same planet. A ball is found at t equals to 0, x equals to 0. After TO, it is still found at x equals to 0. So please consider the three trajectories on the left, which one is allowed by principle of least action. The formula of the trajectory 1 is given by x1 equals to 1/2 GTOT minus 1/2 GT squared. Specifically, I want you to think that both trajectory 1 and trajectory 3 can happen in our world under certain conditions. So why one trajectory happens in one case while the other trajectory happens under some other condition? Finally, as a concluding remark, as in this video we have discussed the possibilities of different worlds. So I want to quote Spirit Breaker, who has traveled between different worlds and has said that one world is much like another.